Hello, AP Chemistry students, and welcome to your Unit 4, Lesson 5 summer work, which is all going to be about bond polarity. So, remember, the Earth has two poles. There's a north and a south pole. And a magnet also has two poles. Well, bonds also may have two poles. And this means that an element has going to be a charge that's going to be different than the other one. So, if a bond is polar, the two elements have different electronegativities. The element with the higher electronegativity is going to be the one that's more negative. So, how do you determine this? Well, first you take the electronegativity difference of the elements involved in the bond. You have your electronegativities in your table S in your reference packet. So, if your bond difference is going to be less than 0.4, then you have a nonpolar covalent bond. If your electronegativity difference is between 0.4 and 1.7, then you have a polar covalent bond. And if you have an electronegativity difference greater than 1.7, then you have an ionic bond. So, hello, AP Chemistry students, and welcome to your AP Summer Work, Unit 4, Lesson 5, which is all going to be about bond polarities. So remember, the Earth has two poles, a north and a south pole, and a magnet also has two poles. Well, so do bonds. Bonds can sometimes have two poles. And if they have two poles, that means that one element has a charge that is different than the other element, kind of like the two ends of a magnet. One is positively charged and the other one's negatively charged. If the bond is polar, the two elements are going to have different electronegativities. Remember, electronegativity is how much an atom wants electrons. And so the element with the higher electronegativity is going to be the one that's more negative in your bond. So how do we figure this out? We could take the electronegativity difference of the elements involved in the bond. So you're going to have to look up the electronegativities on table S in your chemistry reference packet in order to do this. So if you have an electronegativity difference that is less than 0.4, your bond type is going to be nonpolar covalent. If it's between 0.4 and 1.7, it's going to be polar covalent. And if it's above 1.7, it's going to be ionic. So let's talk about covalent bonding. If two or more atoms form a bond with the same electronegativity, the bonds are considered nonpolar. And this means that there is going to be an equal sharing of electrons. If there's an electronegativity difference between the bonds, the atom bonds are going to be polar. This means that they share the electrons unequally, and the electrons are going to hover more around the electronegative atom. And if the bond is polar, the molecule will have a slightly negative and slightly positive side, like two poles of a magnet. So let's talk about molecular polarity. A polar molecule will be asymmetrical, and a nonpolar molecule will be symmetrical in shape and all nonpolar bonds. So let's look at these two. The particle on the top in picture A is water. Water is asymmetrical. It has a slightly negative end and slightly positive ends, which make it polar. And then the two pictures on the bottom, the CCl4 and the BF3, are both nonpolar molecules because they're symmetrical, and the bonds that make up that molecule are also nonpolar bonds. Now let's talk about molecular polarity. When we talk about water, we talk about water being a polar molecule. So like dissolves like. So polar molecules are going to be soluble in water. This is a good reason why, and this is why we can explain oil and water don't mix. Oil is a very large nonpolar molecule. You can see in the picture on the bottom, it's the top layer, and you can see it's a bunch of just carbon chains. And water, it has no carbon in it, and it is polar. So these two things will separate because they're not alike. They're both not the same polarity. So what happens when polar molecules are attracted to an electric field? Well, that is going to help them align appropriately. So as you can see, normal polar molecules are unaligned, so that would be on the top. That's when it's unpolarized. When you put those polar molecules through an electric field, the positive side is going to be on one side and the negative side is going to be on the other side. Now you can see how the molecule flipped. So the polar end, the positive end, is going to go towards the negative charge, and the nonpolar or negative end is going to go towards the other side. So when an electric source comes by, the molecules will quickly align themselves so that their opposite charges attract to the correct electric field side. So now let's talk about intermolecular forces, what we know as IMFs. Intermolecular forces is another name for the bond that keeps elements together in a compound. You have ionic and covalent. Intermolecular forces are attractions that are weaker than bonds but are responsible for holding a substance together. So basically, they're going to hold molecules close to each other. So the stronger the intermolecular force, the tighter the structure is going to be, so it's going to be more solid. The higher the melting point is going to be, the higher the boiling point is going to be. The weaker the intermolecular force, the looser the structure is going to be, so that element's going to be more gaseous, and it's going to have a lower melting point and also a lower boiling point. So there's many types of intermolecular forces, and we're going to run through these real quick because, like I said before, this should be a review. So the first one we're going to talk about is dipole-dipole. An ion dipole, hydrogen bonding, and then London dispersion forces. You might also have heard these called van der Waals forces, but let's start off with dipole-dipole. Dipole-dipole forces are attractions, are strong forces between polar molecules. So they are like a static holding the positive and negative charges together. So when you look down here at the bottom, you have two polar molecules, water on the left and hydrogen chloride on the right, or hydrochloric acid on the right. And that dipole-dipole is going to occur between the positive hydrogen in the water and the negative chlorine in the hydrochloric acid. Then we have ion dipole. This is going to be attraction between a polar molecule and an ion. This is what happens when you have ionic salts dissolving in water. So if you look, the sodium positive ion is going to be attracted to the negative side of the water, the O, and then the chloride ion is going to be attracted to the positive H side of water. And again, it's going to be attracted because you have that positive and negative charge, opposite charges attract. Then you have hydrogen bonding. Hydrogen bonding is a special case. It's the strongest of the bonds, and it is a bond between hydrogen and very electronegative elements, so FON, so fun. Hydrogen bonds are fun. So that is when the hydrogen bond is going to bond with an oxygen, a fluorine, and you can see some examples in the pictures below. Then the last one is London dispersion forces, or LDFs. These are the weakest attraction between nonpolar molecules. They occur between electrons that are going to be temporarily positive and negatively charged. And then the more electrons that a compound has, the stronger the force is. So here's an example between carbon tetrachloride. The two carbon tetrachlorides are going to both be nonpolar molecules, and they're going to be attracted to each other by these LDFs. So when we look at a summary of these intermolecular forces, this chart is a great thing that you should get used to memorizing. So London dispersion, or LDFs, they involve temporary dipole. They occur between nonpolar molecules. They have a low strength. They have a at low elevations, they're going to have high boiling points, and they're going to have low freezing points. And then as you continue down the chart, you can read it yourself. But this would be a good snapshot explanation of IMFs.